Going to start the last section of focus 5. So I'm going to share my screen. Get rid of that. So we're going to talk about activities, which you want to think of activities as just the effective concentration. So how does the solution behave? Does it behave as if its concentration is equal to the true concentration, or is there something changing that? So this will be the last section out of our focus 5, and then we'll move on to actually talking about chemical reactions. So we just have to have this last idea on how we make corrections to our equations, essentially. So we want to think we have a solvent, which is the component that's in the high concentration, and the solute, which is in the low concentration. If we have ideal solutions, then the solvent obeys Réalt's law, where the partial pressure above a solution with some mole fraction of A is related to that mole fraction and the vapor pressure of the pure A. Whereas we remember the solute, that's not true. It's proportional to the mole fraction, but the proportionality constant isn't this. So we'll see that for the solute, we have a different definition of activity. So this equation right here, we know that chemical potential is really the molar Gibbs free energy. And so this is an equation that relates the molar Gibbs free energy to what it would be at its pure state. So when you have A just in solution by itself, that's what the star means, plus the ratio of the new pressure over the pressure that you're comparing it to. So we derived this equation in chapter 3. We did it actually on the board, and I think Marcus did that. So let's go through and think about how we replace the pressures with the activity. So if this is from Réalt's law, then we can rearrange this, and the partial pressure of A divided by the pressure of A, if it was pure, is equal to the mole fraction. So we can replace the pressure ratio with the mole fraction. And once we do that, then we're going to replace the mole fraction with the activity. And so with the effective concentration, so I'll talk a little bit about this when I reach the end of this section, why the solution wouldn't behave as if it just has the concentration that you put in. So if you compare the equations, that means that the activity of A is really equal to the partial pressure of A over the pressure of A if it was pure. The activity is going to go to the mole fraction as the mole fraction of A goes to 1. So that just means essentially that the less disruption you have, so the closer A is to just being pure, the more its activity will match the concentration that you put in. So we usually use something called an activity coefficient to make that correction. So the activity of A is the activity coefficient times the mole fraction. And so now, based on what we said above, the activity coefficient is going to go to 1 as the mole fraction goes to 1. So as you get closer and closer to just pure A, the concentration of A is going to behave more like the activity. We can split this up. So now if we put in for the activity coefficient, and the mole fraction, then you can split those two terms, because we know that the ln of x times y equals the ln of x plus the ln of y. And therefore, this will give us a way to determine this correction experimentally. We'll be able to solve and measure that activity coefficient experimentally. So the activity of the solute, which is the component that's in the lower concentration, if it's an ideal dilute solution, we said it obeys Henry's law. And so now the pressure of B is going to be proportional to the mole fraction, but not by the pure. Instead, it's by some measured Henry's law constant, KB. So that means we can replace, that should be a B. That looks pretty sloppy. The partial pressure of B above a solution is related to the pressure of B above just pure B by the same equation we started with when we derived this for the solvent. But now we're going to replace the total pressure with KB times XB, or the partial pressure, sorry, the partial pressure of B, and then it will be still divided by PB star. So this ratio now replaces this one because the partial pressure of B above a solution is proportional to the mole fraction with that constant KB. So we can do the same things. We can pull out, and now we can redefine our standard state to incorporate these constants, because KB and the pressure of pure B, those are constants. They're not changing. The only thing that's changing in your solution is the mole fraction. So we'll group these two together and we'll call them a new standard state rather than the starred state. And so you get an equation that looks like this, where we've just grouped these two terms together. We redefine our standard state to incorporate those constants, but the chemical potential of B, the solute, is still related to its mole fraction in the same way it was for the solvent. So if the solution is ideal, then KB equals, so then KB, the Henry's law constant, also equals the pressure of B when it's pure. And then it would be true, so that would make this ratio 1, and this term would go away, and your standard state B would also equal your chemical potential of B when it's just pure. So if we have real solutes, though, we can't set those equal to each other because that's not the same proportionality constant. And so we'll replace it with an activity. And now we end up with an equation that looks similar. Just taking what we defined up here and rearranging it and solving for mu B star, putting it in and having an equation where we're comparing the chemical potential of pure B to the chemical potential of B when it has a different partial pressure. And so if we continue to rearrange that, we end up with this equation. And now the mole fraction, or not the mole fraction, the activity of B has a different definition. If it's the solute, it's going to be equal to the partial pressure of B over the Henry's law constant. So this ratio, rather than what we had in the other one, it was the mole fraction. So AB can also be written in terms of an activity coefficient and the mole fraction of B, but now it's going to be different in that as AB goes to the mole fraction of B, or activity of B goes to the mole fraction of B as the activity coefficient goes to 1 and as the mole fraction gets smaller. So if it's the solute, as it gets smaller, this will be true. So stop and do self-test 5F.1 on page 185, just looking at how this might be useful. And then realize that we often don't work in units of mole fraction, but mole fraction is proportional. So the mole fraction of B is proportional to the molality. So in Gen Chem, the molality would have been given a lowercase m, but in physical chemistry, it's given a B. So the molality of B relative to its standard state times the activity coefficient gives you the activity of B if you're working in units of molality, has the same limiting conditions. You're still talking about B as the solute, so you're looking for a dilute solution. So there's a bunch of stuff between here and talking about mean activity coefficients that I'm not going to hold you accountable for, but it is important to think about activity coefficients are most important for ions. And so let's just think about why that's true. So if you have a solution, and for example, you have a +2 cation and maybe some +1 cations, you'd have two, -1 anions. When they're in solution, they're going to try to shield the charge from other positive charges. So if you have a +2 over here and a +2 here, the anions are going to align themselves to try to buffer those +2 charges from each other. And essentially that's why the concentration doesn't behave as if you have as much +2 and -1 as you put in the solution, because there's a lot of arranging of those ions to try to buffer each other, so to shield each other from those large charges. So that's why when you look at the activity coefficients, it's always going to be true that the activity is less than the pure solution's concentration. So that's because you're always going to see a lower concentration because of the effects of how ions will arrange themselves in solution. But if you put something like this, might be calcium chloride in solution, where you have +2 and then 2 -1 anions, you're not going to be able to measure the activity coefficient for the anions separate to the cations, because when you put it into solution, you put both in. So you're always going to measure an average activity coefficient, and so that will just be the product of the two and the square root. So if you want to measure it, you'll look at what the chemical potential would be if it was ideal, and then you can experimentally determine this by looking at how non-ideal it is, whether or not you get the value that matches experiment and theory. So you'll take the average, and it will be for the plus and minus if you have equal number of anions and cations. This is just more general. If you don't have equal numbers of cations and anions, then the activity coefficients will be related to the charge on each of those ions. So when you, so this is equal to, this is equal to the average activity coefficient. So you can measure these, and there are a couple examples in the book if you want to look at them. We're not going to measure them, but it's easy to see that by looking at non-ideal behavior, you can figure out what the activity coefficient is. There are a couple theories, and we're just going to look at Debye-Huckel, and we're not going to derive this, but we're just going to realize that there are a couple of theories that give you pretty good approximations. So the log of the average activity coefficient is equal to -A, and A is just a constant at our at 25 degrees. So we wouldn't know how to do this if we weren't at 25. And then it's going to be the absolute value of the charge on the cation minus the charge on the anion times something called the ionic strength to the 1/2 power. So the ionic strength is really just a sum of all the charges that you have in your solution, because clearly if you have more charged particles, the ionic strength will be higher and you'll have less ideal behavior. So this is essentially telling you how many other competing charges are in your solution. So the ionic strength is 1/2 sum up all of the individual ions contribution. So you have a charge on an ion squared times the molar or the molality of that particular ion, and you're going to add those all up. So the more things you have in solution. So for example, if you were looking at the average activity coefficient for the calcium chloride, if you also had a bunch of sodium chloride in there, you'd have to include those in this term, because the ionic strength is impacted by all the ions, not just the ones that you're calculating the activity coefficients for. There are two other equations that your book shows that are better theory, but the problem is you have to have more correction terms. So I'm not going to ask you to use these, but just to know that there are ways to make this better, but you have to measure these coefficients experimentally. So that kind of defeats the purpose of thinking you could theoretically calculate an activity coefficient. So I think that's the last page. That's the last page. So now we're ready after almost a week and a half. We're ready to talk about chemical equilibrium.